My name is NAWAF Saleh Shahir. Today, me and my group we will explain our project, which is structural design and analysis of one-story residential building. In this project, we will explain and focus on the structural design and analysis of one-story residential building. The primary purpose of the project is to develop safe, economical, and code compliant. Also, the project applies fundamental principles of the structural engineering along with the relevant design standard and code. The objective of our project is to perform structural analysis for one-story residential building under various loading conditions. Also to design structural element as we design it in our project, like slab, beams, columns, and foundation in according with the application design codes. Also to ensure safety, durability, and survivability of the structure, and to design practical and to gain practical experience in the structural design and produce and procedure and calculation. Also to produce clear design documentation including calculation and drawing. The scope of work of our project is preparation of the arithmetical plan of the project and preparing layout of column, beams, and slab. Also determination design load including dead load, live load, and structural element. Analysis of the design of reinforced concrete elements such as slab, beams, columns, and footing or foundation. Verification of structural performance based on the requirement. The project plan is to know load determination, code selection, structural design, verification, and conclusion. We use design code and method. In our project, we use strength design method, SDM, and the ACI code, and also Saudi building code. And the location of our project is in the Kingdom of Saudi Arabia, in Jubail Industrial City, in Al Fanatir. This is the plan view of our project, and the area it is around 188 meters square. Also, we know about the concrete, so we use a concrete in our project. So we have a various type of concrete, like normal concrete, reinforced concrete, lightweight concrete. Also the high strength concrete, and we use also the slab in our project. So we have also the type of the slab, like one-way slab and two-way slab. And in the beam are one of the most important component of a frame structure. It is take the load of the slab and the wall above it. And we have the type of the beams. We have example as we added in our report, like cantilever beam, simply supported beam, overhanging beam, and continuous beam. So we also know about the column. So we have the type of reinforced concrete column, like circular column, rectangular column, L-shaped column. So we explain the column in our project also, and my friend will continue the explanation about the slab design.
My name is Jawad, and I will talk about slab design. In our project, we have 4 slabs. All of them are one-way slab. I will explain how we designed our slabs. For example, slab number 4, we design it with thickness 7.5 inches and ultimate load is 179.7 psi. And we have the reinforcement, which is the main steel, which is bar number 3 at 5 inches center to center, which is the spacing. And we have also the shrinkage steel, which is bar number 3 at 8 inches, which is parallel to longer side, and 5 inches is parallel to shorter side. And now we will explain why we choose this reinforcement number. First of all, you will find the moment from the left negative side and the negative right side and the middle, because it's one-way slab, so we have bending in one way from the left and from the right and in the middle. We calculated, for example, the moment for the left negative side, which is 1.63 kilofeet. Then we will find the reinforcement by this equation. Then we will go to the table A13 to find raw value. The reinforcement came less than the minimum, so we will take raw minimum, which is 0.33. And as we see, we have it less than the minimum in the negative right side also, and in the middle. So we will take raw value 0.0033. So after we have the raw value, we can find the area of the steel by this equation, rho BD. So for the mean reinforcement, we will use rho BD and we will take rho as 0.003 times the base times the depth, which is the thickness minus 1 cover. So we got it's 0.2574. Then we go to table A6, and using this value of AS, we will got that we need to provide bar number 3 at 5 inches center to center parallel to a shorter direction. For the shrinkage reinforcement, since we have grade 60 concrete, we used rho as 0.0018. For this value, the AS is 0.162, and the reinforcement, according to table A number 6, will be bar number 3 at 8 inches, parallel to longer direction. And after applying the checks, it's okay. Finally, the cross section of the slab, as we see, the depth is 6.5, and we have number 3 bars at 8 inches parallel to longer direction, and we have bar number 3 at 5 inches center to center parallel to shorter direction. Finally, the table of slabs. We have each span and each width and each thickness and each steel reinforcement, the mean steel and the shrinkage steel.
So now we will begin the beam design. And for this section, we chose the beam B7, which is one end continuous. Of course, beam B7 and B8 are both one end continuous, fixed at the ends. And we got the thickness to be 16 inches and the ultimate load to be 2.8 kips per foot. So now we will go to the calculations. For the length of the beam, we took 6, which is in meters, and we multiplied that by 3.28 in order to get it in feet, and we got that to be 20 feet. And from the table, for 1, you have the formula to get h, which is the thickness, for one end continuous beams, and it was L over 18.5, and we got that to be 13, and we approximated that to 16 inches. And then we calculated for the width of the beam, which is h over 1.5, and we got that to be 12 inches. And then the effective depth, which is h minus 2.5. Of course, all of these are coming from the 16, and we got that to be 13.5 inches. Then we calculated for the beam weight, which is the volume by the density, and here this is the calculation of the volume. And then we calculated for density, which is a known constant for concrete, and we multiplied it by 10 to the power of minus 3 in order to get it all in kips per foot. And then for the total dead load, we calculated for the beam weight, the dead load from slab 1 and dead load from slab 2, and we got the total dead load to be 1.5 kibs per foot. And then for the live load, we also calculated live loads from slab 1 and live load from slab 2, and we got that to be 0.619 kibs per foot. So for the ultimate load, which is the formula of 1.2 multiplied by the dead load plus 1.6 multiplied by the live load, we got the ultimate load to be 2.8 kibs per foot. And then we started the calculations for the moments. So this is the moment in the right section of the beam 7, and we calculated it, and we got 70 kibs foot. And then you need it after you get the result for that, you use it in order to get the reinforcement percentage, and we took that from the table and we chose 0.00762, and you multiplied that by the beam's width and the effective depth, and you get the area of steel. And after that, from table A4, we chose to provide 3 bars number 7, and then we calculated for the middle moment of the beam, and it has its own formula as well. And then we calculated, which was 80 kibs foot, and the reinforcement was, after you calculate the moment, you divide it by the given formula, and we got 487.7 psi, which is per square inch. And yes, we got the percentage of the reinforcement to be 0.00881, and then we multiply that again by the B and D, which is width and effective depth, as we said, and it results 1.4 inches square. And we chose 3 bars number 7 as well. And then we chose the last one, or we calculated for the last one, sorry, which is the moment of the left section of the beam, and we got that to be 124.4 kibs per feet, or kibs per foot. And then we calculated for the reinforcement, and we got it to be 0.01451, and we did the same calculations again, and we got 2.35 inch squared, and we chose for this one to the 4 number 7 bars with minimum width of 10.9, which passes the JIC requirements, since the width as it's given is 12 inches, so it's okay. And then we calculated actually for the ultimate shear force, which is 1.15 multiplied by the moment, or the ultimate moment multiplied by the length over 2, and we got that to be 32.2 kilo. And then we calculated, obviously, for the design shear force provided by the concrete, so we can see if there are any if any shear reinforcement is needed. And after we calculated that, we get 15.4 kilo. And we, at the end, we got, since the ultimate shear force is more than half of the design shear force of the concrete, then shear reinforcement is needed. And we provided number 3 bars with two-legged stirrup at 6.5 inches center to center. And this would be the cross sections for both beam 7 and 8 at the decided sections of C, E, A, D, and B, and their respective reinforcement.
Design of the column. We designed for column 11 with ultimate load of 52 and ultimate moment of 45. And the size of the column is 12 into 14, and the tiles is 3 bar, 2 legs at spacing of 6.5 center to center. First, we start with the moment by finding nominal axial strength, which equal to BU over theta equal to 52 over 0.65 equal to 80. And the nominal moment capacity, which equal to mu over theta, and it is equal to 45 over 0.65, and it is equal to 69 kilo feet. We convert it to kilo inch by multiply it by 12 and it is equal to 828 kilo inch. Now for finding the gamma and the Rn and Kn, to use it in the diagram to find the percentage of the steel. First we start with the gamma equal to H minus 5 over H, which is equal to 14 minus 5 over 14, and it is equal to 0.64. We make it 0.6 to use 0.6 diagram. And now for the Rn, which is equal Mn over Fc dash into Bh square, equal to 828 over 4 multiplied by 12 multiplied by 14 square, which equal to 0.09. And now for the Kn, which is equal to Bn over Fc dash into Bh, which equal to 80 over 4 multiplied by 12 multiplied by 14. And it is equal to 0.12. Now for the diagram, referring to Rn and Kn, we find the percentage of steel 1.25%. We use it to find the area of steel, which equal 1.25 into 12 into 14 over 100, because it is percentage 1.25 percentage, which equal to 2.1 inch square. Now from table A4 we provide 8.5, which is equal to 2.45 inch square. Now for tie design, we design ties for 3 bar 2 legs. So first we take the spacing by 48 tie bar diameter, which is equal to 0.375, and it is equal to 18. Then 16 into long bar diameter, which is equal to 0.625, and it is equal to 10. Finally, the least lateral column dimension, which is equal to 12. We choose the lowest number, which is 10, for designing. Now we check the spacing, which is equal to 14, the long dimension, minus 2.5 minus 2.5, the cover from both sides, over 2, the number of spacing, minus 0.625, which is the long bar diameter, and it is equal to 3.9, and it is less than 6 inch, so it is good for the designing. Now for steel percentage, and we take it as 1.25%, and it is less than 8%, so it is good. And the number of long bars are 8, which is more than 4, so it is good for the designing. And this is the cross section of the column.
Assalamu alaikum wa rahmatullahi wa barakatuh. I'll be taken after Hussein, and I am going to explain the foundation design. This is an isolated footing, and this foundation, we are given some data as of the depth of foundation, which is 4 feet, and the soil unit weight, and the allowable soil pressure on the soil, and QU, which is the axial load of the column above the foundation. So first we need to assume a thickness of the foundation itself. After that, we are going to find QE, which is the allowable soil pressure, and we subtract the pressure of the soil and foundation after above the soil above the foundation, or below the soil below the foundation, sorry. So after finding QE, we find the size or the area of the foundation by taking PU over QE, and we are getting an area. This area, we can see that 4 multiplied by 6 is the closest to 20, which is 24. So after that, we need to find the factored bearing pressure for design of concrete, which is QU. To find QU, we take PU over the area, which will give us a pressure of 2.17 kibs per square feet. So now we are checking for one-way shear. For the one-way shear, we need to find the higher shear force on either this shaded area or this shaded area. This area we multiply it by QU to find the larger shear force. So from this calculation, we found that this is the larger area. We multiply it by VU. After that, we are getting the shear force on that area, and this is the shear force equation. We just manipulate it to get D outside. So we can see that D is 1.59 inches, which is less than 8, so this is okay. Now we need to check for the two-way shear. So we need to find this shaded area and we multiply it by QU to get the shear force. So this shaded area by this and we multiply it by QU, we are getting the shear force. This is B naught, which is the area of the column, and we add to it the as a parameter surrounding the column, which D over 2. It's D over 2. So this is the area. We need to find this area as B naught. So now we are going to put B naught, which is the parameter surrounding the column, in the shear equation. After putting it in the shear equation, we are getting D of 2.8 inches, which is less than 8, so this is good. Now we need to find the reinforcement alongside the x-axis. So first we are taking 6 over 2, which is the length of the foundation alongside the x-axis, and we subtract the length of the column alongside the x-axis by 2. So we are getting this L1. This L1 we multiply it by QU multiplied by the 4 multiplied by 2.42 divided or 42 to the power 2. This whole thing is divided by 2. Now we have the moment. From the moment we can calculate Rn, which is 0.33, which is less than 192.2. Therefore we take the minimum ratio of reinforcement. After that we need to find the area of reinforcement. We take the ratio, multiply it by the cross-section area of the foundation. After that, from table A.4, we can see that 7 number 4 bars will give us an area of 1.37, which is more than the needed, therefore it's okay. So we do the same for the reinforcement alongside the y-axis, and we can see that 10 number 4 is the reinforcement that we are going to put in the foundation alongside the x-axis. So in conclusion, the structure element satisfy ACI and SPC codes, and the load transferred safely to the ground as shown in the calculation, and the design is suitable for residential building as all the calculation is taken with respect of the building as a residential building. So these are the reference, all the information taken from them, and in the end, thank you for listening and have a great day. Thank you.